Hello students, so today I will explain the structural elucidation and synthesis of geraniol. In my previous lecture I explained about the structure and the synthesis of citral. So let's see about this geraniol structure and its synthesis. So the structure of geraniol which we have to prove is like this. This is the structure of geraniol. Okay, so in my previous lecture I told you how this can be obtained. This can be obtained by the reduction of citral. So this was the citral, and if we reduce it in presence of sodium and amalgam, then we can get this geraniol. And one thing that we should keep in mind, that the citral is this is a trans citral, not the cis one. So this is a trans citral, and this geraniol is also the trans one. Okay, so the name of this trans citral, this can also be written as a geraniol. It can also given the name geraniol, Al. Okay, this is Al. And this is geraniol. Which can be obtained after its reduction when it is converted into this primary alcohol which is present over here. Okay, so if we see this structure, then there is one of the allylic alcohol group which we have to prove. Two double bonds are present. The position of these two double bonds. Another thing, this is a monoterpenoid and acyclic one. Okay, so overall what we have to prove? We have to prove first this molecular formula, then whether it is the two double bonds are present, it is a acyclic one, the oxygen is in the form of alcohol, and it is allylic alcohol. Okay, so let's see the structural elucidation. Okay, so first if you will see the molecular formula, then molecular formula of this was determined to be C10H18O, and we know that in monoterpenoid 10 carbon atoms are present. So no doubt this is a monoterpenoid because 10 carbon atoms are present. And if we determine the double bond equivalent, so by formula we can determine it. So how many double bond equivalents are there? 10 number of carbon atom minus number of monovalent atom, that is hydrogen, divided by 2, plus there is no trivalent atom or nitrogen atom, so that can be taken as a 0, and plus 1. Finally we write as a 1 here. So the overall, what should be this double bond equivalent? It is equal to 2. This is equal to 2. 2 means either 2 double bond may be there, or 2 rings may be present, or combination of 1 double bond plus 1 ring. So we already, because I have already drawn the structure here, so what we have to prove? 2 double bonds, and we have to also prove that there is no ring. So now the presence of this 2 double bond. Third, the presence of double bond. Presence of 2 double bond. So how this presence of 2 double bond or unsaturation, that can be proved by the hydrogenation. So if we have this geraniol, that is C10H18O, then if we do the hydrogenation in presence of palladium or platinum, then it will undergo reduction. And 2 molecules of hydrogen, it was found that two molecules of hydrogen get attached to this formula. So finally the formula can be written as C10. The formula which was obtained was C10H22O. So if four hydrogens are attached over here in this structure, so what we can write the name? This is tetrahydrogeraniol. So name that we can write is tetrahydrogeraniol. Okay. Now further, one more experiment. If it is this in presence of Br2CCl4, if bromine and test was done, then the molecular formula that was finally found, that was C10H18O, and this is Br4. Okay, so this is tetrabromogeraniol, or we can write it name tetrabromogeraniol. Okay, so it means this geraniol contains two double bonds. Okay, it means two double bonds are present, or we can say there is no ring, only two double bonds are present. So it means therefore two double bonds are present. Two double bonds are present, that we can write. Okay, now fourth test that we can do, that is the nature of this oxygen atom. Okay, one of the oxygen atom is present in this molecular formula, and what is the nature of this oxygen atom, or analysis for this oxygen atom? So nature of oxygen atom. Okay, nature of oxygen atom. Now if we do the test, suppose one of the tests that can be performed is if we do the test of steric ammonium nitrate. Steric ammonium nitrate test. For alcohol, we know that this, if steric ammonium nitrate test is positive, then it shows the presence of alcohol. So steric ammonium nitrate test. So this was found to be positive. It means the presence of this alcohol. And second, if it is reduced, if it is oxidized, suppose this C10H18O, that is this geraniol undergo oxidation. If it is undergo oxidation, then what we got? We got this citral. We got the citral. So citral was obtained. So if citral was obtained, and citral is the alpha beta unsaturated aldehyde. Citral was obtained, which is alpha beta unsaturated aldehyde. So it means, so the formation of this alpha beta unsaturated aldehyde group in this citral, it confirms the presence of one of the allylic alcohol group. It means if alpha beta unsaturated aldehyde group is present in this citral, then it means this OH is the allylic. So this is OH is the allylic OH. So it means OH group is allylic one. Is allylic alcohol. So OH group is allylic alcohol. So these two tests, these are the two tests, and third, whether it is a allylic alcohol. As this is allylic alcohol, another test that was done. So if we have this citral, and if it is treated with manganese oxide as an oxidizing agent, then this manganese oxide is a chemoselective oxidizing agent, and it can only oxidize the allylic alcohol. Okay, it can only oxidize the allylic alcohol, and after that the product that was obtained, was the citral. Okay, so this MnO2 is the chemoselective oxidizing agent. Chemoselective oxidizing agent. Okay, so in this way we have proved that this OH is the primary alcohol, and it is a allylic one. Okay, and it also shows one of the position of the double bond also. Now let's see. Now next point that we can prove is the acyclic nature of this geraniol. Geraniol is acyclic one. Okay, so we have formula C10H18O. Now if we convert it into the saturated hydrocarbon, or we for determining whether it is a acyclic one or cyclic one, we convert the molecular formula into the saturated hydrocarbon or into the parent alkane form. So if we add, because it was proved that it contains the 2 double bond, that's why to convert this into the saturated one, then we should add 4 hydrogen. Okay, because this formula it contains 2 double bond, that's why to make it the saturated, okay, we should add 4 hydrogen. So after adding this 4 hydrogen, the formula that we get is C10H22. Okay, so we have to only see about the cyclic and acyclic nature. I am not writing this oxygen here. So this formula corresponds to the general formula of CnH2n plus 2, and if the formula is CnH2n plus 2, this general formula, this corresponds to the acyclic nature, acyclic nature. So it means this monoterpenoid, this is a acyclic monoterpenoid. Okay, so what we have proved up to now, we have proved the 2 double bonds, presence of 2 double bonds, position and the nature of this oxygen atom, which is a allylic oxygen OH group, allylic OH group, and third one, this is acyclic nature. Now next, as these 2 double bonds are present, so we have to prove this position of these 2 double bonds. So let's see the position of double bonds, and we know that this position of double bonds that can be proved by the oxidative degradation analysis. So let's do the oxidative degradation analysis. Okay, now if we do the oxidative degradation of this geraniol, first in presence of alkaline KMnO4, so it will, the double bond that would be converted into diol, or it is a cold alkaline KMnO4, so that would be converted into diol. So one of the OH group here, another OH group we can write over here. This is OH, this will OH. Okay. Now further oxidation in presence of this chromium oxide. So degradation will occur, and the the bonds will break from here. So we can write this bond will get broken, this bond will get broken, and it will undergo oxidation. So means how can we write the product after this chromium oxide oxidation? So means we may add one of the OH group over here. After breaking this bond, add one OH group over here, okay, another OH group over here. In the same way, we may add one OH group here. After breaking, we may get another OH group over here, and remove the H2O, and remove this H2O. We can remove this H2O. Okay, so what we will get if we remove this H2O? Finally, what we can get here? So we have broken this bond from here. We have broken the bond from here. So this part can be written as one of the product that will be obtained is ketone. So that will be converted into this part, that will be converted into ketone. Okay. This carbon atom has one of the hydrogen already present over here, and that will be converted after removing this H2O. After removing this H2O, this C and this carbonyl that will be formed. C double bond O that will be formed. So what we can write here? We can write, so one of this carbonyl group that will be formed. Hydrogen is present. This one of the hydrogen is present. COH. So CHO that will be formed. Okay. CHO means here that would be converted into CHO. That would be converted into CHO, and this group that will be converted into, also that will be converted into ketone. So after the removal of this H2O from here, this is converted into ketone. Okay. Now finally, again this oxidation of this will takes place, and we can write the product. Okay. COOH. So this would be the final product. And the next product that is formed is CH2OH, and this will be converted into, after the removal of H2O from here. After the removal of H2O from here, we will get the CHO over here. So this carbon will be converted into aldehyde, and again after oxidation, that will be converted into COH. This CH2OH, that is also converted into COH. So three products, we will get the three products. This is one of the product, this is another product, and this is the another product. So the oxidative degradation is giving you these three products. So again I am writing it. So write it. So these three products can only be obtained when the position of these two double bonds are, one of the double bond should be present over here, another double bond should present over here. Then only we can get these three products. So after this, it will form a diol. This will form a diol, and this bond will break, and after the breaking of bond, one of the product that we will get, this is keto. Another product, this carbon will be converted into, first it will be converted into CHO, and then that will be converted into COH. This carbon that will be converted into keto form, and here these two carbon, so this carbon will be converted into COH, and this carbon will also be converted into COH to get this oxalic acid. Okay, so the formation of these three products, it tells about the position of these two double bonds. So in structural determination of this geraniol, so what we have proved, first this molecular formula, that is C10H18O. Then by the hydrogenation test, presence of two double bonds, okay, by hydrogenation and by bromination test, the presence of these two double bonds, and then the nature of this oxygen atom by steric ammonium test. Okay, then by oxidation of this, it giving you the citral, and then the oxidation using the MnO2, which tells the presence of this allylic this alcoholic group, and further the position of these two double bonds. This is proved by this oxidative degradation analysis. Okay, so now further, finally, the geranoil, the structure of geranoil, this is proved by the synthesis. So let's see its synthesis. Okay, so we have to synthesize this molecule, that is geraniol. We have to synthesize the geraniol molecule having C10, number of carbon atom is 10, H18 and this O. We have to synthesize this one. Okay, so how can we synthesize this one? So what should be the reactant molecule taken so that we can synthesize the geranoil? So for this, the reactant molecule which were taken, that can be also determined by the retrosynthetic analysis. So suppose if we break this one from here, then if you break this one from here, then one of the reactant molecule that we may take is allyl bromide. We can take one of the, this is allyl bromide, and it contains 1, 2, 3, 4, 5 carbon atom. This is 5 carbon atom compound that we can take. Another molecule that we can take for this synthesis is ethyl acetoacetate. We may take ethyl acetoacetate. This is 1, 2, 3, 4 carbon compound. This is 4 carbon compound. And third reactant molecule that we may take is CH3MgBr. This is the 1 carbon compound. So we should have 10 carbon atom. So for this 10 carbon atom, this is one of the reactant molecule that we may take. This is the another reactant molecule, ethyl acetoacetate, and this methyl magnesium bromide that can be taken as the another one. So using these, let's synthesize the geranyl molecule. So first of all, we have allyl bromide and ethyl acetoacetate. Okay, so this is ethyl acetoacetate, and we may write this ethyl acetoacetate in its enolic form. So let's write it in an enolic form. So I may write it in enolic form. Okay, and double bond present over here. Now what we can do, in presence of some base, suppose lithium diisopropylamide, LDA, in presence of this base, this is one of the strong base, it can abstract one of the hydrogen from here. So after abstracting one of the hydrogen from here, then here we will have the negative charge, and this negative charge, this will tap over here, and this bromine will leave out. Okay, so what we will get here, so I may write the product. Here we will have the oxygen atom, and further we have double bond over here. This is a double bond, and from this double bond one methyl group is attached over here, and COET group is further attached to this. So this is our COET group, CO2ET group. So we should keep in our mind the structure of this geranyl. So while synthesizing this molecule, we should keep in our mind the structure of this geranyl. So what we have got here, this is this type of structure, which is somewhat, this is similar to this geraniol. Now further what we may do, so we have to remove the oxygen from here, and if we match this one with this geraniol, original geraniol molecule, then we should also have the, in place of this ester group, we should also have the CH2OH group. So how can we put a CH2OH group in place of this ester? By reducing agent. If we reduce this ester group by any reducing agent, then that can be converted into the this one. And further, this one double bond is present similar to this structure, and here we have to remove this oxygen also. So this structure is similar to this is vinyl and this is allyl group. This is the vinyl group, this is the allyl group, and this is one of the ether. So it is allyl vinyl ether. So this is allyl vinyl ether, and we know that this allyl vinyl ether, it undergo 3,3 Claisen rearrangement. If we have done this pericyclic reaction, then it may undergo 3,3 Claisen rearrangement. Okay, rearrangement. Now, so this is first carbon, this is the second carbon, this is the third carbon. Similarly, this will be the first one. This is first, second and third. This is first unsaturated element. This is the another saturated element, which during this pericyclic reaction we can number in this way. So first, second, third, and this is first, second, third, and the bond breaks from this between these two saturated carbon, and new bond that would be formed between this 3 and 3. That's why it is 3,3 Claisen rearrangement. The new bond will be formed between this carbon and this carbon. Okay, so this is 3,3 Claisen rearrangement. Now, so in presence of heat, it will undergo the rearrangement. And how? So this bond will break. CO bond, no doubt, the CO bond will broken out. So this will break from here, and this will go here, and further this bond will go. So what we will get finally, we will get, if you will see, then this is oxygen, this will have a double bond over here. Now this will be converted to single bond, CO2 and now new bond is formed at this third position. New bond is formed from here. So, and okay, so this is now, this bond is converted into the single bond. This is now a new single bond which is formed, and here this is converted to double bond. This bond is converted into double bond, and this will be the product formed. Okay, now in next step what we have to do, so here we should not have this oxygen, right? So this I should write it for my convenience. I will write it like this. I will write it in this way. This is the double bond and CO2 ET. I have put this carbonyl group over here, and finally so for my convenience I have written in a different form. Now what we have to do, now if I convert this one into this CH2OH, okay, if I reduce this ester into CH2OH, then that will also be get reduced. So that's why this carbonyl will also get reduced if we reduce this ester group into CH2OH. Okay, so we have to put we should have a CH2OH group, but here we have ester group. So if we reduce this one, then this will also get reduced. That's why we should protect this keto group. So now protection. So protection of keto group. Protection step, And the keto group in protection group chemistry, I have told you the keto group can be protected either 1,2-diol, 1,3-diol or thiol also. So I am taking ethane diol. I am taking ethane diol and using some base is some acid, suppose para PTSA, I may take paratoluene sulfonic acid as a acid. Now, so what we will get? So this keto that would be converted into the cyclic. This would be converted into cyclic. This ET. Okay, so in place of this keto group, I have protected it, and now what we can get further? So after protection, now we can convert this ester group into the CH2OH group. For this, suppose I may take lithium aluminum hydride. And this will first reduce it. This can reduce it into the finally in keto form and then into this form. So this will get fine. So this will get reduced to finally it will get reduced into this alcohol. So now I can write it. Okay. Now, so this is being converted into this one. Now, in next step, what I will do, in presence of acetic anhydride, this OH, I will do the acetylation of this OH. So I will tell you why I have done the acetylation. Though we want this OH group over here, we have got this OH group over here, but I am doing the acetylation. So why I will tell you. So I am doing the acetylation first. Acetylation OAC, and so I have done the acetylation. Now we may do the deprotection. So for deprotection we may add some acid. In presence of some acid, it will now undergo deprotected. So it can undergo deprotection, and finally, so that would be converted into keto again. Now what I will do, you may see that in place of this keto group, I have to bring the methyl group. So methyl group may be added by using this methyl magnesium bromide. In presence of methyl magnesium bromide, in place of this keto, we will have the methyl group and OH group. Okay, so let's see. Now we may add methyl magnesium bromide, and we will have one of the OH group over here, and this is methyl OAC. Clear? Now what we have to do further? What should we do further now? Now what should we do? Okay, so it will undergo dehydration. This OH group is present. So in presence of thorium oxide, this may undergo dehydration. So this thorium oxide, it may give you the Hoffman product. So one of the H is present over here. Suppose one of the H is present over here. So this H and this one, this will undergo, okay, so we will have now a double bond over here. So I may write a double bond. and OH. Okay. So the double bond the double bond may be present over here. Okay, OH from here and one of the H can be removed from here also. But this thorium oxide especially, it gives the Hoffman product. So this is, we may write, it is giving the Hoffman, not the Sedgwick product. It is giving the Hoffman product. Okay. Now this may undergo the co-rearrangement. So what we have to do, we should have this carbon-carbon single bond over here. So to make a carbon-carbon single bond over here, we can do the co-rearrangement. Co-rearrangement. Okay, so in presence of heat, this will undergo co-rearrangement. So how we can, again, this is the saturated carbon, this may will give a number 1, this is number 2, 3 and 1, 2, 3. So 3-3 rearrangement that will occur again, 3-3 rearrangement, and if you will see, then this one will go over here, this may here, and this bond, one bond that will break. Okay, so what we can write, we may write, this is the double bond, is present over here, OAC, and new single bond is formed, double bond is converted into single bond, new double bond is formed. Okay, here we have a new double bond, and okay, so that this we have got. Now in next step, so what we can write it in another way. This is, we can write it in a similar to this geraniol. If we write it, then what we have got actually. Now, so this OAC, that can be converted into this OH. So if we have to bring a OH, OH group. So KOH hydrolysis can be done. Okay, in presence of KOH hydrolysis. So now this can be written. This can be converted into this OH group. So these are some steps for the synthesis of geraniol. Now let's come to the isomerism in geraniol. So let's see. Now, isomerism in geraniol. Okay, so now if we reduce this citral, after reducing this citral, so this was the citral, and after its reduction, we get geraniol as one of the product, and nerol. This is the nerol. Okay, so this is geraniol. This is geraniol and this is nerol. So these two are the product. Okay. Okay. So now, so how can we confirm at these are the two. This is one of the trans product. This is trans isomer and this is the cis isomer. This is cis isomer and this is trans isomer. So the formation of this cis isomer and trans isomer, this is confirmed. This is confirmed by, if we heat this in presence of H2SO4. If we heat this geraniol and nerol in presence of H2SO4, then it gives the alpha terpenoid. Okay, it gives the alpha terpenoid, and this formation of this nerol, or from nerol to alpha terpenoid, that reaction is much faster in comparison to the when geraniol converts it into the alpha terpenoid. Okay, so let's see what is the product. So product, what I told you, if we in presence of H2SO4, it gives this both will give the alpha terpenoid. So this is the alpha terpenoid, and this can be obtained from geraniol as well as from nerol. So this is the geraniol, this is transformed, and this is nerol, and this is cis form. This is nerol, which is in cis form. So if we this trans geraniol in presence of this H2SO4, it gives alpha terpenoid. It gives alpha terpenoid, and nerol in presence of H2SO4 also gives the alpha terpenoid. But here this nerol is converted into this alpha terpenoid 9 times faster. This reaction is 9 times faster, okay, in comparison to this one. So all we can say, the cyclation of this nerol into this alpha terpenoid is 9 times faster cyclization. Okay, so from here it was, so why this 9 times faster reaction? Because here this OH is much closer to this double bond. This OH is much closer to this double bond where the cyclization can occur. So that's why we can say that this nerol is in cis form, where with here, as this OH is far away from this double bond. Okay, these two are far away. This OH and this is far away. So the cyclization will be slower, where this cyclization will be faster. So like this. So now we will see the mechanism how this nerol can be converted into the alpha terpenoid also. Let's see the mechanism also. So this is the isomerism, and further it can also be proved by the NMR study also. This cyclization, this isomerism can be proved. Now let's see some application of this geraniol. So we can prepare the other terpenoids. We can prepare the other terpenoids using this nerol or geraniol. So transformation of nerol. So this is the uses. We can say uses of application. Transformation of nerol into alpha terpenoid that I told you just now. Citronella. This is another one of the this limonene into this alpha terpenoid, limonene, and alpha pinene. Okay. Let's see its transformation. So if you will see, we have nerol, this is nerol, and this is cis form, cis nerol we can say. Now, in presence of this H2SO4, this oxygen, this will be protonated, and what we may write? We may write here OH2, and positive charge will come over here. Now further, this will get removed, H2O molecule that will be removed, being the good leaving group, and this would be converted into positive charge will come over here, and like this. Okay, in next step, this bond, so cyclation will occur to remove this positive charge, and we may write now this positive charge will come over here, this will undergo cyclization, and this will be the product. Okay, so now this can be converted into either alpha terpenoid. So if this is further in presence of H2O, OH2 plus, and finally after the removal of this H plus, we may write the alpha terpenoid. Okay. So you have seen that this nerol can be transformed into the alpha terpenoid. So this transformation is much faster, 9 times faster in comparison to if we take the here Geraniol, that is the transform. So cis nerol, its conversion into the alpha terpenoid is much faster than the transform. So this is our alpha terpenoid. Now this alpha terpenoid, now this can give the another product also. If we remove H plus from either this carbon or this carbon, then that may give the limonene also. So this is the another terpenoid. Okay. Now next we can also transform into the alpha pinene. So how this alpha pinene? So this may be this structure. This structure I am writing this structure into, for convenience you may write it in this way also. We may write this structure in this form also. We may write in this form also. And finally, just I have inverted this form into here. I have inverted to this position to this position. And now this positive charge that can be removed. And the new positive charge that will be present over here, and we may connect this bond to, and these are the two carbons. Okay, now in next step what may form, it may give after the removal of H plus. So H plus can be removed from this position, either from this position or from this position. H can be removed from this position, or H may be removed from this position. So no doubt I will remove it from here. Otherwise, if the double bond is formed over here, then that would not be stable. So as the double bond is not stable over the ring, over this bicyclic ring, so what you may find at this point. Okay. So this is the structure of alpha pinene. Okay. So we will also see the structural elucidation and the synthesis of pinene also. So like this is about the geraniol. Okay, thank you.